In this example, we'll use facts we know about complex numbers to help us factor a polynomial. We want to use complex numbers to help us factor the following polynomial: x to the 10th plus x to the 6th minus x to the 4th minus 1 equals 0. So how are we going to factor this? Well, as it is right now, it doesn't look too great using complex numbers to do this. What we can do first, we can factor this by grouping using our normal algebraic techniques and then see where that gets us. So seeing that the gap here is 4 powers of x, and the gap here is also 4 powers of x, that means factoring by grouping might be the way to go here. So we're going to factor an x to the 6th out of the first two terms and see what happens. So doing that, I get that this is x to the 6th times an x to the 4th plus 1 minus x to the 4th minus 1 was the same thing as x to the 6th times x to the 4th plus 1 minus 1 times x to the 4th plus 1, 0. Or by grouping, x to the 6th minus 1 times x to the 4th plus 1 equals 0. Now, based on our normal rules for factoring polynomials, the zero product rule, if this is going to be 0, then either something on the left or something on the right must be 0. So either we have x to the 6th minus 1 equals 0, or x to the 4th plus 1 equals 0. And we'll handle these two cases separately. So for x to the 6th minus 1 equals 0, this becomes x to the 6th equals 1, and this falls right into our roots of unity that we discussed previously. So we know what these roots look like. Right? These roots should all be of the form e to the I times 2 pi k over 6, because I'm doing 6 roots here, for k from 0 up to 5. Or because we're doing 2 pi k over 6, that's also k pi over 3. So my roots here are 1 for k being 0, e to the I pi over 3, e to the I 2 pi over 3, e to the I 3 pi over 3, which is e to the I pi, which is minus 1, e to the I 4 pi over 3, and then e to the I 5 pi over 3. Now, how does this help me factor this expression? Well, because 1 is a root and minus 1 is a root, I know that x plus 1 and x minus 1 are both factors of x to the 6th minus 1. So I know that then x to the 6th minus 1 is going to be x minus 1 for the 1 as a root, x plus 1 for the minus 1 as a root, and then some fourth order term, where this fourth order term has roots at the 4 non-real complex numbers above. How do we find this fourth order term, or in particular, the two quadratic terms it will factor into? The first thing we notice is that because these have complex roots, these will give me irreducible quadratics. In order to get a real quadratic out of the equation, I have to multiply two conjugate roots to give me a real polynomial at the end. This is the fact that we know that if a real polynomial has a complex root, it also has its complex conjugate as a root. So if I'm going to get real polynomials, which is what I want to multiply these roots in conjugate pairs and see what I get. So what does that mean? Well, let's look at these roots now in rectangular form and see if that helps. So the roots we had were 1, which is still 1, e to the I pi over 3. My x-coordinate should be cosine of pi over 3, which is 1/2. And the y-coordinate, or the imaginary part, should be sine of pi over 3, which is root 3 over 2. For 2 pi over 3, I get the same y-coordinate, but a negative real part, because now that I'm doing cosine of 2 pi over 3, cosine is negative. So I get negative 1/2 plus root 3 over 2i. Minus 1 is still minus 1. E to the I 4 pi over 3. Now we're in the third quadrant, so both are going to be negative. And then for e to the 5 pi over 3, I'm in the fourth quadrant, so I will have a positive x and a negative y. Now we can see a conjugate pair of roots here and here because only the imaginary part has changed sign. So how do we get the polynomial that gives rise to those? We multiply those out like we would have factored them normally. So the polynomial that gives rise to those two roots should be x minus 1/2 plus root 3 over 2i times x minus 1/2 minus root 3 over 2i. Just like the polynomial that gave rise to the 1 as a root was x minus 1, and for minus 1 was x minus negative 1 or x plus 1. You can do it the same way. But since these are complex roots, they're going to show up in pairs as quadratics and as irreducible quadratics over the real numbers. So now we just expand all this out. If I FOIL this out, I get x squared minus an x times 1/2 plus root 3 over 2i minus an x times a 1/2 minus root 3 over 2i, and then plus 1/2 plus root 3 over 2i, 1/2 minus root 3 over 2i. The fact these are complex conjugates will make this next part always happen, and that's that the imaginary part's going to cancel out of the x term. Right, on the first I have a minus root 3 over 2i, next I have a minus negative root 3 over 2i, so those are going to cancel. So when I put this together, I get x squared. This is going to give me a minus x from the two 1/2s. And this last here is a difference of two squares, because it's a plus bi and then a minus bi. So I'm going to get 1/2 times 1/2 is 1/4 minus the other one squared, which is a 3/4 times I squared. I squared is minus 1, that becomes a plus sign. So I get x squared minus x plus 1 as a quadratic polynomial here. Now I can do the same thing with the other pair of conjugate roots here and here, writing them out the same way. And I can work out the exact same algebra, and the same cancellation in the middle here, and the same different squares at the bottom gives me the polynomial x squared plus x plus 1. So basically swap the minus in the second term there for the plus sign. That's because the minus sign that I get on the 1/2 when I take the other set of roots. Now, what does all this tell me? Well, all of this put together tells me that I can factor x to the 6th minus 1 as x minus 1, x plus 1, x squared minus x plus 1, and then x squared plus x plus 1. I'm basically now taking all of the roots and all the polynomials I get from those roots and combine them all together. We had the x minus 1 from 1 being a root, the x plus 1 from minus 1 being a root, and then the two irreducible quadratics coming from the two different pairs of complex conjugate roots that we found via roots of unity. That's half of my problem. The other half is dealing with the x to the 4th plus 1 term. Well, this becomes x to the 4th equals minus 1, and we know how to find that using roots of complex numbers. -1 is e to the I pi. I'm going to want to divide that by 4. Again, the radius here is all 1, so I'm not going to have any weird things there. But I'm going to divide everything by 4, and then adding 2 pi each time. So from this, I will get that my roots should be e to the I pi over 4, e to the I 3 pi over 4. When I add 2 pi, I get a 3 pi on top dividing by 4. E to the I 5 pi over 4, and e to the I 7 pi over 4. Now, none of these here are real numbers, so in order to find any of the polynomials to factor this, we're going to need to write them all in rectangular form and then multiply the complex conjugates together like we did before for the two irreducible quadratics on the x to the 6 minus 1 case. So in rectangular form, these roots are, well, pi over 4 is at 45 degrees. Its x and y are the same, so it's just going to be 1 plus I over root 2. 3 pi over 4 will be minus 1 plus I over root 2, and the same goes for the rest of them. And again, as expected, we see two pairs of conjugate roots. We see this pair here and this pair here. We can now again use this to figure out these quadratics that these give rise to. So for the first pair of roots, we have these two factors. I can then fold it out like before. Again, the imaginary parts cancel from the x term because they have opposite signs. And this then becomes x squared minus 2 over root 2x plus, this will be a 2 on the bottom, and then a 1 plus 1 on top, so a 1 here. So x squared minus root 2x plus 1. Now it has a root 2 in it, which is fine. It's not like a rational polynomial, but it's still a real polynomial. We are allowed to do things like this. We can also work the same thing out for the second pair of roots. And as you'd probably expect, you work this out and you get x squared plus root 2x plus 1 in the exact same manner as before. So this here then tells me that I can factor x to the 4th plus 1 as x squared minus root 2x plus 1 and x squared plus root 2x plus 1. So then with now everything sorted out, I can now write out the final answer here. So we have x to the 10th plus x to the 6th minus x to the 4th minus 1. We saw factors as x to the 6th minus 1, x to the 4th plus 1. And then our work above showed we could factor each of these separately again, giving an x minus 1, x plus 1, x squared minus x plus 1, x squared plus x plus 1, all coming from the x to the 6 minus 1 term. And then the x to the 4th plus 1 gave me an x squared plus root 2x plus 1, and an x squared minus root 2x plus 1. And that gives us a way to factor this polynomial into linear terms and irreducible quadratic terms. Why is this helpful? Well, these are terms we need to do partial fractions. Right, this is what we needed to do a partial fraction decomposition of a function. If we can now factor things like this way, we could then break this up for partial fractions, plug it all in and solve it all out. And here it'd be super useful to have complex numbers, because then you can make each one of these terms all go to 0, in which case you only have at most 2 coefficients solved for at any one time in the equation. The issue with not having complex numbers before was that all of these terms added more complexity to how you solve this problem. With complex numbers, you can eliminate every term in here by plugging in a certain number, and that will make it so you don't only have to solve for 2 coefficients at a given time. It's probably very long to do that way, but now that we know how to factor polynomials into both linear and irreducible quadratics using complex numbers, it becomes possible to solve problems like this using partial fractions and using other methods you have to solve these sorts of equations.